ELT. What discoveries will the world's largest telescope give us? In Chile's Atacama Desert, the extremely large telescope, the world's largest telescope, is being built. It will be equipped with an optical lens of more than 39 meters in diameter, occupying an area larger than a basketball court. Thanks to this, it will have a sharpness and range superior to those currently held by the Hubble Space Telescope, and even more incredible than what the new James Webb Telescope will offer. Keep watching to find out more. One of the main objectives of the ELT telescope is the discovery of new extrasolar planets and the study of the atmospheres of these planets. It will also be reasonable for studying the protoplanetary disks in other stars to understand better how solar systems arise, as well as studying dark energy and galaxy formation. The telescope is currently under construction. Although the pandemic caused setbacks, the European Southern Observatory, ESO, has announced that if the work continues uninterrupted, the telescope will be completed in 2027, starting its operations in September of that same year. Structure. The extremely large telescope is the next largest optical telescope in the world. Currently, that title belongs to the Very Large Telescope, a set of 4 mobile telescopes located at the Paranal Observatory in the Atacama Desert in Chile. The ELT is being built on the Amazones, since it is one of the best regions on the planet for astronomical observation, because it has clear skies 300 days a year. There is practically no rainfall nor much humidity, and it is located more than 3,000 meters above sea level. Thanks to this, there are very few air particles that interfere with the observations. But despite being in such a high area, the ELT is still within the atmosphere and is therefore susceptible to perceiving atmospheric turbulence. Atmospheric turbulence. In astronomy, atmospheric turbulence is the interference that occurs in the images obtained by telescopes when air particles overlap in the images. Remember that the atmosphere is a medium in which a great variety of gases are found. These gases work as a fluid that distorts the images we see in the night sky. It is for this reason that we see the stars as if they are flickering. But the stars do not twinkle. What happens is that the gases in the atmosphere stand between our eyes and the light of the stars, and in the end, after the light passes through the entire atmosphere, we perceive a distortion, diffuse, and trembling image of the stars. This is also why astronomical observatories are placed in high places like mountains or volcanoes. The less atmosphere between the telescope and outer space, the less atmospheric turbulence. Although this optical effect is striking and a source of inspiration for poets, it is a severe problem that interferes with astronomical observations for astronomers. The easiest way to avoid atmospheric turbulence is by leaving the Earth, since in space there is no air and therefore no atmospheric turbulence, which is why telescopes as necessary as Hubble or Kepler were placed in the area so that they could observe the stars without interference caused by the gases of the Earth. However, this is not the only way to combat atmospheric turbulence. It's also possible to avoid it through adaptive optics, which will be implemented by the ELT. Adaptive optics. Adaptive optics is a system in which sophisticated computer-controlled deformable mirrors are used to correct the distortion caused by atmospheric turbulence in real time. However, there is a slight drawback. This technique only works if there is a star with a very intense brightness near the object we want to study, and it is not always possible to find stars like these anywhere in the night sky. Fortunately, there is a straightforward way to solve this, creating artificial stars. Astronomers can create artificial stars by emitting a powerful laser beam into the upper layers of Earth's atmosphere. This excites sodium atoms located 90 kilometers above sea level in the atmosphere and creates an artificial star. They are not real stars. They are only an intense source of light which serves as a reference that helps us measure the atmospheric aberration of the Earth at that point, and at that particular moment to correct it with the deformable mirrors. The deformable mirrors are made of Zero-Dur, a unique ceramic glass material manufactured by Schott, a German company. Each sheet of Zero-Dur, 35 millimeters thick, is polished by the French company Sarafan Rios, making it a flexible segment less than 2 millimeters thick, much thinner than human hair. Subsequently, the segment is placed on the surface of a huge mirror, and more than 5,000 magnets are glued to the rear surface of the mirror. This system is the key to the operation of the flexible segments, as it is responsible for making more than 1,000 adjustments per second with an accuracy of 50 nanometers, as small as the tiniest of viruses. Thanks to this system today, it is possible to observe practically the entire sky with adaptive optics, but the pioneers in this technology are ESO scientists. Currently, adaptive optics are used in the VLT and soon in the ELT. The challenge of building the world's largest mirror. One of the biggest challenges facing the ESO team is the creation of a 39-meter diameter mirror. To understand why it is difficult, you have to remember the force of gravity. As you know, gravity is that invisible force that keeps us all subject to the Earth and what causes things to fall down and not up. Well, this same force causes weighty objects to deform. Thus, a mountain weighing thousands of tons is distorted by the force of gravity, only that this deformation is invisible to the naked eye. It is only detected when we measure it with high-precision devices. That's where the problem lies. Telescopes are high-precision devices that can perceive these deformations. To make large telescopes, we must also make huge mirrors. Still, since the 60s, astronomers realized that from 3 meters, the lenses of a telescope began to be incredibly heavy, to the point that from 5 meters, gravity deformed the mirrors and lenses of telescopes. This deformation is because as they make larger lenses, they also become heavier, weighing several tons, and therefore gravity crushes and deforms them, even if they are solid. To build mirrors of more than 5 meters in diameter, it was necessary to build massive structures to support the mirrors, considerably increasing construction costs and resulting in extreme forms without any guarantee of improvement in the image. Adaptive optics. To solve this, ESO engineer Raymond Wilson invented a system called adaptive optics, a thin, deformable one that replaces large, heavy mirrors. The idea of a deformable mirror was already thought of since the 19th century. Still, it was impossible to conceive since no system could correct deformations by gravity in real time. Everything had to be done by hand, and a telescope mirror that must be deformed is not very reliable or perhaps possible. But in the 21st century, with the advent of computer technology, it was possible to create an active support system made up of hundreds of pistons controlled by a computer that would apply the necessary force on the mirror to correct gravity-induced deformations. The first telescope to use this system was the NTT, New Technology Telescope. Thanks to active optics, the NTT's 3.58-meter primary mirror is only 24 centimeters thick and weighs 6 tons, instead of weighing more than 10 tons like its counterparts that do not use the adaptive optics system. The corrections applied by the actuators are calculated in real time thanks to a computer with an image analyzer that detects even the most minor deviations from the ideal shape of the mirror. Thanks to this, we managed to counteract the deformations caused by gravity. This system was later used in the VLT to also correct atmospheric turbulence. In addition, it was possible to build mirrors of 8.2 meters in diameter, which weigh more than 11 tons, but are only 37 centimeters thick, while telescopes that do not use this technology came to be more than 1 meter wide without having so much range. The new ELT will also use active optics technology, but carried on an unprecedented scale with a mirror of 39 meters in diameter. Although building such a large mirror is a practically impossible task, since at this scale the slightest movement can break the entire mirror, instead what is done is to build a mirror divided into segments that, when placed next to each other, generate the image of a single mirror. The ELT will consist of 798 individual segments that together will form the image of a single mirror. Each of these 798 individual segments can be moved using a piston mechanism and tilt corrector, making this mosaic work as a single gigantic mirror, compensating for the effects of fluctuations caused by temperature, gravity, and atmospheric turbulence, providing even better images than space telescopes give us. Scope. With all these implements, the ELT is contemplated to be able to observe in the spectrum of visible and near-infrared light, that is, the same frequencies in which the James Webb Telescope will follow. In this way, both will compete to demonstrate which of the two manages to capture the best images of the universe. But above all, beyond the competition that may exist, both telescopes will collaborate and work together to study very distant bodies in the universe at the same time. This way, if either telescope gets images of some mysterious or essential object, such as a distant galaxy or an exoplanet, the other telescope will point its mirror at that object to get even more information. The ELT will have 6 different mirrors, and each one will fulfill another function. However, according to ESO scientists, the 6 mirrors will be able to work simultaneously to obtain more information about the object being studied. This will allow it to have a range like no other. It is expected that with the ELT, it will be possible to observe the early universe as the most distant galaxies of the universe, stars that are too far away in our galaxy, and of course, planets orbiting other stars. Expected discoveries. Among the discoveries expected by the ELT when it becomes operational are tracking Earth-sized exoplanets around other stars in habitable zones where life might exist, fundamental contributions to cosmology by probing the nature of dark matter and dark energy, study and discovery of small black holes, study the behavior and evolution of distant galaxies, visualize the first galaxies that emerged in the universe in the so-called Dark Ages, the earliest epoch of the universe only 380,000 years after the Big Bang, study and discover small bodies in our solar systems such as asteroids, comets, objects in the Oort cloud, and a possible 9th planet. Although it may not seem like it, all these research areas still have a long way to go. Some of them are relatively new, such as the case of the study of exoplanets, which is just over 20 years old. ELT will provide us with a new light to understand all these phenomena of the universe and at the same time provide technology that will be of great help to other telescopes around the world. Remember that the ELT will only be able to probe the south of the sky and a part of the north, so it will be necessary for telescopes in the northern hemisphere, such as those found at the Mauna Kea Observatory in Hawaii, USA, to also implement these technologies to have a complete picture of all the mysteries that are in every corner of the sky. Finally, it should be mentioned that the ELT will be a pioneer in the implementation of new technologies and new systems that will help us to study the universe better. So this is just the beginning of a new generation of telescopes that will provide us with the tools we need to understand better how the universe began and how it could end.